so now we'll move on to some vector algebra. Okay, so we're going to start. I'm going to start by naming two vectors. So here's V, which is composed of AB, and then W is CD, let's say. Okay, so these are just numbers, right? So let's say V looks like this. Okay, so here's vector V, and vector W looks like that, or something like that. Actually, I'll say something like that, okay? So here's V and there's W. And basically what we're going to do is do some algebra, play around with these vectors a little bit. So first we're going to do addition, okay? So we're going to do V plus W, all right? And this, pictorially, what it's going to look like is we're going to take V, okay? And what you do is you take the first vector, so we have V already. Okay, so I drew that, and then to add W, you take the base of W, so this little point that I just drew, and you stick it onto the end, onto the head of V. Okay, so we're going to base W here and continue drawing that. Okay, so here's W, right? And our resultant vector is formed by where we started in the very beginning, so the base of V up to the very ending. Okay, so where the head of W is. So this new vector that I just drew here is called V plus W. Okay, so that's actually a new vector. And algebraically, the way you work this out component-wise is you just add the two x components, so that would be A plus C to get our new x component, and then you do the same thing with the y component, so B plus D. Alright? Okay, so now let's do the opposite. We have subtraction. Okay, so let's say we have V minus W. Okay, so what we're going to do is the same thing, except for there's a little twist, right? Okay, so we have vector V. Okay, here's its base. So there's V. And then now we're going to take W, and let me rewrite this a little bit to give you a little hint on what we're going to do next. So we have V, and it's kind of like we're adding the opposite of W. And remember, opposite means you flip the vector around and you have it pointing in the other direction. Okay, so here's W. Remember, it was pointing to the right and a little bit down. What we're going to do is flip it around. And so here is negative W. Here's the vector negative W. And now what we're going to do with that is add this negative W onto V. So we're going to have the base here, and we're going to have it pointing like that, like so, okay? So V, that's actually a bad position for it. So V is this, right? And here's our negative W. And so our resultant vector, our V minus W vector, is the one I'm drawing in right now. So this one pointing straight up, okay? That is V minus W, okay? And component-wise, again, we'll do that. So V minus W means the x component of V minus the x component of W. So A minus C. And then we'll do the same thing with the y's, B minus D. B minus D. Okay? Alright, so that's it for addition and subtraction. And now we'll go on to scalar multiplication. So I'll put the title here. So scalar multiplication. Okay, so what is a scalar, first of all? So scalar basically just means it's a real number. Some real number, okay? And it's the opposite, or you can kind of consider it like just the opposite of a vector, not a vector quantity, not a vector. Okay, so no arrow, no arrows going on here, okay? So here, let's say V is, I'll give it actual numbers, so 1, 2. Let's say this is V. So a scalar multiple, so a scalar multiple, and I'll abbreviate, of V looks like the following. Looks like, and frequently now we'll use a Greek letter called lambda. Okay, so lambda, and then we have our V. So lambda is just a variable that stands for a number. Okay, so an example would just be maybe like 2 or something, let's say. So let's say we have 2, lambda equals 2. So a scalar multiple of V would be 2V, and the way we would compute that is 2 times 1, the components 1, 2, alright, and this 2 basically just distributes in, okay? multiplies in, so our resultant vector is just going to be 2, 4. And if we draw this, let's say we have the vector v, right? So that's 1, 2. Okay, that's inaccurate. So it's going to go like this. Let's say we have our x and our y. 1, 2, 3, 4. 1, 2, 3, 4. Okay, so our original one, v, looks like this. 1, 2. And now our resultant one is 2, 4. So now it'll end up over here. Okay, so this one, again, it's based at the origin, but now, I can't draw lines to save my life. Hold on. Okay, so it's going to stand all the way up to 2, 4. So here was our small one. That was just v. And then our long one is 2 times v. So as is demonstrated in this picture, the v, because you multiply it by a scalar, it doesn't, it's pointing in the same direction, just as long as, so I'll write this down. So same direction if, there's a condition here, if lambda is positive, which means greater than 0, right? But we're going to say opposite direction, opposite, if lambda is not 0, but if it is less than 0. Because then that would mean it's negative, right? And a negative sign brings in the flipping motion, right? So even if we have a lambda as -1, it would look like this. It would flip across, okay? It'd still be on the same line. Scalar multiples are always lie on the same line as the original vectors, but if you have that negative, it'll just flip it and point it in the other direction along the line, okay? Okay, so now let's consider one more thing that happens in when you're doing scalar multiplication. So what happens to the magnitude? So we'll write magnitude, what happens to it when we have some scalar multiplication going on? So what's going to happen? So let's take the example of 2 times v. This was 2 times 1, 2, which ended up being 2, 4, right? Okay, so we'll take this example and we'll kind of extend it to other things. So the original v, it had components 1, 2, right? So the magnitude of that, let's see, magnitude of the original v was 1 squared plus 2 squared, okay? And that's going to be square root of 5. So that's the original one, the short one. And then let's take the magnitude of 2v. So if we take magnitude 2v, so this is our scalar multiple here, we're going to take these components and square them. So 2 squared plus 4 squared, all right? And that is going to be a square root of 20, okay? Which is also equal to square root of 4 times 5. So we can take out a 2, and then we have our square root of 5 here. So, as you can see, because we added this 2 and we multiplied by 2, it actually shows up in our magnitude as well, right? Because our magnitude ended up being 2 times the magnitude of the original v, okay? Because the magnitude of the original v was square root of 5, and here it is again. So we can take this example here and kind of generalize it. So if we have basically the magnitude, so I'll just write a little rule here. So magnitude changes, we'll say, changes, not necessarily increases, because if your lambda is actually like a fraction or something, your vector is going to get smaller in length. Okay, so magnitude changes by a factor of not lambda, but of the absolute value of lambda, okay? Because, for example, let's say we were to do -2v, all right? So, again, this is important, the absolute value of lambda, not lambda itself. But anyways, so I'll take the example, what if lambda were to equal -2? Then we'd have the vector -2v, all right? And if we take the magnitude of that, since we're squaring the components anyways, it's not going to matter. And we're actually going to get the same thing of 2 radical 5, okay? So that's where we get this absolute value from, okay? Okay, so now I'm going to introduce a new topic involving vectors, and that is of linear combinations. So linear combinations. All right, so let's say, again, I'll draw a couple of vectors here. So let's say we have vector v. Okay, so this is vector v and vector w, all right? that's this one over here. Okay, so basically what a linear combination is, so I'll abbreviate linear combo of v and w, basically means that it gives, so it is a vector given by the following formula. Given by r times v, the vector v, plus s times vector w, where r and s are scalars. And again, scalars just mean are scalars. That just means real numbers, okay? Like 2 or 3 or something like that. Or even like fractions, like 2.5 or something. Okay? So what that means is that we have this r and s, which are like coefficients for our vectors. And you know how, okay, so let's say, for example, I'll show you another example on the next slide. So let's say we have 1/2 of v plus 1/2 of w, okay? So in this case, r and s are both equal to 1/2, okay? So here were our original v and w. So here was v, let's say, pretend this is a straight line, please, and this is w, okay? So there's w. So half of v would be half its length, right? So here's half of v. Half of v is this little one, and half of w would be about here, okay? So there's our half of w. And when you add them, you basically just take one and shift it to the top of the other. So here I'm moving it like that, like so. And so here's our half of w. Sorry if this is a little bit confusing, the picture. But here's our half of v, ending right here, and half of w. So our resultant vector is going to be this one right here, okay? It's going to stick straight in the middle of our of what would be the parallelogram of the bigger vectors, of the original vectors, okay? So it's going to be right here. So this is the linear combination that we're looking at, okay? So now we're going to try to extend this idea to reach a bigger conclusion. Okay, so let's say, again, we're going to start with our v and w. So here's our v, all right, and then here's our w. Okay, so we're going to take this, and the big parallelogram, remember when we're adding vectors, we basically just get, if we stick w on the top of v here, we get this, all right? And then similarly, if we were to do w plus v, so here's v, then we get to the same, we reach the same outer corner up there, right? So this, regardless, is going to be this long line that I just drew there. That long vector is going to be v plus w, okay? And that forms our parallelogram. So v plus w, another way to rewrite it is just to stick in ones here, right? That doesn't change anything. These are equivalent. Okay, so in this case, our r is 1, and our s is also 1, if we're looking at this from the linear combination perspective, okay? So by making r and s both equal 1, we can reach this outer corner of our parallelogram. If we look on the other side, like at the other end here, the other point of our parallelogram right here, our r would have to equal 0, and so would our s, right? Because then we would have 0 times the vector v plus 0 times the vector w, so you just get the 0 vector, which is this corner. It doesn't go anywhere, it just stays at 0, right? And then, let's say, again, let's look at our 1/2 v plus 1/2 w. Remember, that ended somewhere in the middle here, actually, because we had half of v plus that half of w here, so we ended about here, right here on this vector. So the point that I'm trying to get at is that you can hit every point inside this parallelogram here with some linear combination of v and w. So, yes, so generally, with this linear combination formula, so r times vector v plus s times vector w, we see the extreme cases, right, when r is 1 and s is 1, so it reaches all the way to this corner here, the top right, over here. And we see when r and s both equal 0 as well. That means you're at the bottom left corner down here, right? And if you have either one of the r, like let's say r equals 1, then you have just the v vector, so we get this corner. And if you and this is with s equaling 0, right? Because we're adding 0 of w to it. And then if on the other hand you have s equals 1 and r equals 0, then you just get the w vector here, and we get this corner. Okay? So what I'm trying to say, the generalization I'm making, is that when r and s stay between 0 and 1, and here's s, between 0 and 1 as well, this gives you, having these conditions here, along with this formula for the linear combination of the vectors v and w, this will allow you to hit all of the points within this parallelogram, okay? You can hit all of those with combinations of v and w, basically taking part of v with part of w and creating these vectors here, okay?